We're now going to look at the effects of these radioactive particles on the human body and on biological materials. So one very useful way to use radioactive particles in medicine is to actually include them in compounds that are then ingested or injected or inhaled in the human body. And what happens is, since our body uses biological compounds, we take in sugars and proteins and so on, if we can replace one of those atoms in a protein molecule or a sugar molecule with a radioactive isotope, so replace carbon-12 with carbon-14, for instance, in a sugar molecule or something similar, when we consume or ingest or inhale that radioactive isotope, it decays in our bodies. Now, normally that's a bad thing because those alpha, beta, or gamma particles that are given off can destroy surrounding tissue. But, especially for gamma particles, gamma radiation can actually pass pretty easily out of our bodies, so we actually can make our bodies glow in gamma rays. So what we can then do is these tagged compounds, when you add a radioactive isotope to a particle, we call that particle tagged, and these tagged particles are often referred to as radiopharmaceuticals. Pharmaceutical being, again, a drug, radio being it's radioactive. Now, once you have consumed a radiopharmaceutical, and who would consume a radiopharmaceutical? Well, cancer patients. Unrestricted cell growth, for instance, hyperthyroidism, bringing in extra iodine into the thyroid. Well, if you include a radioactive isotope of iodine, then you can identify in the thyroid where cancer cells might reside. Or other types of cancers, bone cancers and so on, you can introduce radioactive compounds to see where tumors might exist in the body. So by doing that, there are multiple ways of doing this. One is called an Anger, or more often referred to as a gamma camera. So if you have a radioisotope that gives off gamma rays, those gamma rays are then brought into a gamma camera. It's basically just a series of very, very thin tubes where the gamma rays must be coming directly in to hit the camera. So you get a detailed two-dimensional mapping of the tumor, but there's no depth or three-dimensional information. You can get three-dimensional information from the next two types of scans. You probably have heard of these, especially if you work in the medical profession. A SPECT camera or a PET scan, a PET camera. Single photon emission computed tomography works very similar to a CT scan does with X-rays. So it looks at individual gamma ray emission, and from that emission can reconstruct a three-dimensional image of the irradiated or the radiation or tagged compound. This is a slow process and also doesn't have great resolution. I think your book limits it to about 1 centimeter or so. And then there's finally positron emission tomography. Now this is interesting. PET cameras are interesting because you put in a radioisotope that gives off a beta plus particle or a positron. That positron will quickly strike a nearby electron, creating two gamma rays. Those gamma rays have equal energy and they move away from each other in a straight line. So if you have a camera surrounding the patient and you can detect both gamma rays, you know on the path where that gamma ray came from, and when the gamma rays arrive, if you can time that, you know approximately where on the line the gamma rays emitted from. So if the gamma rays arrived exactly at the same point in time, you know that the emission had to have occurred exactly in the middle of that line. The resolution on these PET scans are a bit higher resolution, about 0.5 centimeter or so, compared to a SPECT camera. But all of these are useful in determining possible tumors in the body by, again, tagging radiopharmaceuticals, putting those radiopharmaceuticals into the body. Your body naturally absorbs, depending on the type of tissue that you're looking to see, which is cancerous. Pick one that organ uses, and then you can see tumor cells, cancer cells usually are more active. They're quicker reproducing, so they can bring in more of that tagged isotope and allow you to see where that tumor occurs. So radioactive materials are useful, but again, ingesting radioactive materials is not a good idea except for these diagnostics. You don't go in and consume or get injected with radioisotopes unless your doctor thinks something might be seriously wrong. Because putting in a radioactive material into your body can damage the surrounding tissue. And we'll talk about that in a moment.